Hello. Today I'm going to talk about the rest of set 14, which is series review, with the exception of problem 8. But I'll try to make this quick and then do a quick video on problem 8. Hopefully we'll see how that works. So, as I mentioned last time, we don't want to use that formula for Cn, the coefficient in front of x to the n, unless we have to. And in fact, we've gone through and we can compile a bunch of results and refer to them. These are kind of like subroutines that have already been written in our program. Okay, so last time we talked about the Taylor series or Maclaurin series. These are all Maclaurin series, Taylor series centered at 0. Maclaurin series for 1 over 1 minus x is just the geometric series. And then you learned all of these in Calc 2. The Maclaurin series for the log of 1 plus x is, I can write it with summation notation like this. And this minus 1 to the n plus 1 gives me an alternating sign. But if I write it out, it kind of makes more sense. It's x minus x squared over 2 plus x cubed over 3 minus x fourth over 4 plus dot, dot, dot. And this holds for x between minus 1 and 1. It doesn't hold it when x is minus 1, because I'd be taking natural log of 0, which you can't do, undefined. But it does hold when x equals 1. In fact, this is a neat way to see that if when x is 1, I get 1 minus a half plus a third minus a quarter plus a fifth, etc. That's equal to log 2. All right. Then there's a few more series that are known. The series for the arctangent of x. That's another alternating series. X minus x cubed over 3 plus x fifth over 5 minus x 7 over 7, etc. All right. Then you might remember if I plug in x equals 1, I get a series that converges to arctangent of 1, which is pi over 4. That was another cool fact. Okay, then there's sort of a dividing line here, because these are all derivable from this one. I do things like I integrate, or I substitute in x squared for x, and then integrate all that stuff from Calc 2. But then we can get these series, and actually these series are easily defined and originally defined from that formula for Cn is the nth derivative of f evaluated at 0 over n factorial. We can get all of these. But after we've done them, we just use them. First, the series for e to the x, 1 plus x squared over 2 plus x cubed over 3 factorial plus x fourth over 4 factorial, etc. Very useful. Cosine and sine are very similar, except they have an alternating sign, SIGN, okay, pluses or minuses, and the cosine only has even powers of x, and the sine only has odd powers of x. In fact, that's something you can think about. And any even function in its Taylor series would only have even powers of x, being non-zero. And every odd function only has odd powers of x. Okay, so you don't have to write all this down. I mean, you can, but it's on the web. You can search, I'm sure, for a place where a bunch of series are defined. So I'm going to get rid of a lot of them and start working on some of these problems. All right, so I want to start by talking about substitution. I did this yesterday, but suppose we said, let's find the Maclaurin series for, let's say f of x is, let's say 3 sine of 2x. Well, I just use this guy here. I just substitute in 2x for x, and I get 3 sine of 2x is going to be 3 times sum from n is 0 to infinity minus 1 to the n times now 2x to the 2n plus 1 over 2n plus 1 all factorial. Okay, and then I can bring this in as n equals 0 to infinity of minus 1 to the n. Then I can say 3 times 2x to the 2n plus 1 all over 2n plus 1 factorial. Okay, now that's fine as it goes, and one of the WeBWorK problems actually has you match this function with that or something very similar. But actually, I would probably use this one at the bottom. I would probably say, I would just use this. I would keep the 3 in front and then just use 2x minus 2x all cubed over 3 factorial plus 2x to the 5th over 5 factorial minus, I guess I want to keep going to do a point here. Okay, so what I've done here is I've just used the series. Then the first few terms are all I need, right? So I'm using sine of the thing minus the thing cubed over 3 factorial plus the thing to the 5th over 5 factorial minus the thing to the 7th, etc. So let's write this out a bit. I get 6x, and then when I do the 3, this is going to be 2 cubed here. I get a minus sign. I'm going to get 2 cubed here, and I'm going to get 3 times 2, so 2 cubed gives me 2 squared. This is going to be 4x cubed when it's all done, right? Because the 3's cancel, one of those 2's. And then for the rest of it, I don't want to keep, I'm not going to simplify these too much. Three. Okay, all right. So here's the series for this function f of x is 3 times sine of 2x. All right. So let's now let's suppose the question is find T4 of x, the Taylor polynomial. That's a capital T for Taylor. For that same function, f of x is 3 sine 2x. Okay. Well, T4 of x is, I've written out 4 terms here, and you might be tempted to just write this whole thing in there. You say, well, there's not enough room in the box in WeBWorK. But remember, T4 means there's the Taylor polynomial of degree 4. It doesn't mean 4 non-zero terms. If I asked for 4 non-zero terms, I have to plug in the whole thing. But if I want T4, that's just 6x minus 4x cubed. That's T4. Why is it T4? Because it's 0 plus 6x plus 0x squared minus 4x cubed plus 0 times x4, period, right? I don't see all these 0 terms, but T4 is a polynomial that includes up to the x to the fourth term. And if the x to the fourth term is 0, I don't have to write it. So it's kind of weird. I call this a polynomial, Taylor polynomial of degree 4, but it's actually a polynomial of degree 3 in this case. So we probably should call T4 the Taylor polynomial of degree at most 4, or something like that. But that, we don't want to get that, right? So that's kind of the weird thing. So you have two different problems. One says to ask for, say, 4 non-zero terms in the Taylor polynomial with 4 non-zero terms. And then the other one asks for Taylor polynomial T4. Okay? So be careful on that. All right. So